Look up on a clear afternoon, anywhere on Earth, and you will see blue. Not the blue of painted walls or colored fabric, but something altogether different. A blue that seems to come from everywhere and nowhere at once. A blue that shifts and changes as your eyes move across the dome above you. A blue that has been there since long before humans walked upright and will remain long after we are gone. Most people, if asked why the sky appears this particular shade of blue, will offer a quick answer. Something about molecules, perhaps. Something about scattering. Some might mention a physicist's name they half remember from a classroom years ago, and on the surface, these answers seem sufficient. They feel complete. But the truth sits deeper than these simple explanations allow, woven through multiple layers of physics, chemistry, and biology that all conspire together to create the exact shade of blue your eyes perceive when you look upward on an ordinary day. This is not a mystery that requires traveling to distant galaxies or peering into microscopes at realms invisible to human sight. The explanation exists in the space between the sun and your retina, across approximately 150 million kilometers of vacuum, through roughly 100 kilometers of atmosphere, and finally onto the neural pathways that interpret electromagnetic radiation as the concept your brain calls color. And embedded in this explanation are principles that govern how our universe operates at scales both enormous and impossibly small. So settle into whatever position feels comfortable. The journey ahead will move slowly, deliberately, building understanding layer by layer. There is no urgency here. The sky will still be blue when we finish. It was blue yesterday and will be blue tomorrow. But by the time we reach the end, you will hold knowledge that 99% of people never acquire. You will understand not just what makes the sky blue, but why the simple answers fall short. Why the complete answer requires weaving together insights from multiple scientific disciplines, and what this reveals about the extraordinary complexity hidden in phenomena we encounter every single day without a second thought. The atmosphere through which you are looking right now is performing continuous physics experiments. Every photon of sunlight that enters from space undergoes transformations as it encounters air molecules, ozone molecules, and various particles suspended in the gaseous mixture we call breathable air. Some photons reach your eyes after a relatively straight journey. Others bounce between molecules multiple times before arriving at your retina. Still others scatter away entirely, never reaching you at all, instead illuminating someone else's patch of sky on the other side of the world. Understanding why the sky is blue means understanding why more blue photons reach your eyes from directions away from the sun than red photons do. It means understanding the size of molecules relative to the wavelength of visible light. It means understanding how the sun produces its light, how that light travels through the atmosphere, how molecules interact with electromagnetic radiation, and how your eyes and brain transform that radiation into conscious perception. We will move through each piece carefully. This is not a race toward an answer. This is an exploration of how multiple truths combine to produce a single, observable phenomenon. And the explanation will probably surprise you because it turns out the simple answer most people give is not wrong, exactly. It is just incomplete, profoundly incomplete. And the missing pieces matter more than you might expect. If you search for why the sky is blue, or ask someone with a passing interest in science, you will almost certainly hear about Rayleigh scattering. This is the name attached to a phenomenon discovered and mathematically described in the late 1800s. The explanation typically sounds something like this. Sunlight contains all colors of the visible spectrum, and when this light enters Earth's atmosphere, it encounters air molecules. These molecules scatter light, but they scatter shorter wavelength light more efficiently than longer wavelength light. Blue light has a shorter wavelength than red light, so blue light scatters more. Therefore, when you look up at the sky away from the sun, you see more scattered blue light than scattered red light. The sky appears blue. This explanation contains truth. The scattering described here absolutely occurs. Air molecules do indeed scatter shorter wavelengths more efficiently than longer wavelengths. Blue light does have a shorter wavelength than red light, and Rayleigh scattering is a fundamental part of why the sky appears blue. But if this were the complete explanation, the sky would not appear blue at all. It would appear violet. And yet, when you look up, you do not see violet. You see blue. This single discrepancy reveals that other factors must be at work. The Rayleigh scattering explanation, by itself, predicts the wrong color. It predicts a sky shifted further toward the short wavelength end of the visible spectrum than what we actually observe. So either the Rayleigh scattering model is incorrect, which seems unlikely given that it has been verified through countless experiments and observations, or additional phenomena are combining with Rayleigh scattering to produce the final result we perceive. Scientists in the 1950s began investigating this discrepancy more carefully. A physicist named Edward Hurlburt published research demonstrating that at certain times of day, particularly during sunset, ozone absorption in the atmosphere contributes as much as 2/3 of the blue color we observe overhead. This finding complicated the simple Rayleigh scattering story considerably. It suggested that the atmosphere is not just scattering light, but also absorbing certain wavelengths, and that this absorption contributes significantly to the final color our eyes perceive. More recently, researchers have identified that at least 4 distinct factors combine to produce sky color. Rayleigh scattering is one. But the thermal spectrum of the sun itself matters. The way light attenuates as it travels through the atmosphere matters. The absorption characteristics of ozone matter. And, perhaps most surprisingly, the sensitivity characteristics of human cone cells matter. The color you see is not just a property of the atmosphere. It is a property of the interaction between the atmosphere and your specific biology. This realization shifts the question slightly. We are not just asking why the atmosphere scatters light in particular ways. We are asking why the combination of atmospheric scattering, atmospheric absorption, solar radiation characteristics, and human visual system characteristics produces the specific perceptual experience we call blue sky. This is a more complex question than it first appeared, and answering it requires understanding each component in turn. The journey ahead will take time. We will need to understand what light actually is at a fundamental level. We will need to understand the composition and structure of Earth's atmosphere. We will need to understand how molecules interact with electromagnetic radiation. We will need to understand the sun's radiation spectrum. We will need to understand ozone and its absorption characteristics. We will need to understand how human eyes detect and interpret light. Only after assembling all these pieces can we finally provide a complete answer to the seemingly simple question: why is the sky blue? So let us begin with the most fundamental question of all. What is light? Light is strange. It behaves sometimes as a wave and sometimes as a particle, depending on how you measure it. It travels at a fixed speed through vacuum, approximately 299,792,458 meters per second, but slows down when passing through materials like glass, or water, or air. It carries energy from place to place without requiring any medium to travel through. And it comes in an enormous range of wavelengths, only a tiny fraction of which are detectable by human eyes. The technical term for light is electromagnetic radiation. This name reveals its nature. Light consists of oscillating electric and magnetic fields that propagate through space. These fields are perpendicular to each other and perpendicular to the direction of travel. As they move forward, they oscillate up and down or side to side, creating a wave pattern that can be described by a wavelength and a frequency. Wavelength is the distance between 2 consecutive peaks in the wave. For visible light, wavelengths are measured in nanometers, with 1 nanometer equal to 1 billionth of a meter. This is an almost incomprehensibly small scale. A human hair is roughly 60,000 to 80,000 nanometers wide. A single oxygen molecule, which we will discuss extensively later, measures about 0.1 nanometers across. Visible light wavelengths fall between roughly 380 nanometers at the shortest end and 750 nanometers at the longest end. Frequency describes how many wave peaks pass a fixed point in space per second. Frequency and wavelength are inversely related. Shorter wavelengths correspond to higher frequencies. Longer wavelengths correspond to lower frequencies. And because light always travels at the same speed in vacuum, if you know the wavelength, you can calculate the frequency and vice versa. The relationship between wavelength and energy is particularly important for understanding sky color. Shorter wavelength light carries more energy than longer wavelength light. This is not intuitive from everyday experience because we do not directly perceive the energy content of individual photons of light, but it becomes relevant when we consider how light interacts with matter. Higher energy photons can cause different effects than lower energy photons when they strike molecules or atoms. The visible spectrum, the range of electromagnetic radiation wavelengths that human eyes can detect, spans from about 380 nanometers to about 750 nanometers. Different wavelengths within this range trigger different responses in the photoreceptor cells in our retinas, and our brains interpret these different responses as different colors. Violet light occupies the shortest wavelengths in the visible spectrum, roughly 380 to 450 nanometers. These are the highest energy visible photons, oscillating at the highest frequencies. Moving up the wavelength scale, we encounter blue light, roughly 450 to 495 nanometers. Then comes green light, approximately 495 to 570 nanometers. Yellow light spans roughly 570 to 590 nanometers. Orange light covers 590 to 620 nanometers. And finally, red light occupies the longest visible wavelengths from about 620 to 750 nanometers. These boundaries are not sharp. There is no precise moment where blue becomes green or green becomes yellow. The transitions are gradual, and different people perceive the boundaries slightly differently based on individual variations in their eye biology and neural processing. But the general pattern holds across all humans with typical color vision. Short wavelengths appear blue or violet. Long wavelengths appear red or orange. Medium wavelengths appear green or yellow. The sun produces light across the entire visible spectrum and beyond, extending well into the ultraviolet at short wavelengths and well into the infrared at long wavelengths. When sunlight contains all visible wavelengths mixed together in roughly equal proportions, we perceive it as white light. This is what you see when you look at a piece of white paper in sunlight. The paper is reflecting all visible wavelengths relatively equally, so your brain interprets the mixture as white. But the sun does not actually produce equal amounts of every visible wavelength. Its output follows what physicists call a black-body spectrum or thermal spectrum. This is the characteristic pattern of electromagnetic radiation emitted by any object based purely on its temperature. The sun's surface temperature is approximately 5,500 degrees Celsius, and at this temperature, the sun's peak output occurs around 500 nanometers, right in the middle of the visible spectrum in the green region. However, the sun produces substantial amounts of light at wavelengths both shorter and longer than this peak. The spectrum is not a spike at 500 nanometers, but rather a broad curve that extends across the entire visible range and beyond. Importantly, for our purposes, the sun produces somewhat less violet light than blue light, somewhat less blue light than green light, and somewhat less ultraviolet light than any visible wavelength. This non-uniform distribution will become important when we try to understand why the sky is not violet. When sunlight travels through the vacuum of space toward Earth, it does not change. Photons emitted from the sun's surface travel in straight lines at the speed of light, carrying their specific wavelengths and energies unchanged across the approximately 150 million kilometers between the sun and Earth's atmosphere. But once sunlight encounters Earth's atmosphere, everything changes. The atmosphere is not empty space. It is a mixture of gases, primarily nitrogen and oxygen, along with smaller amounts of argon, water vapor, carbon dioxide, and various other trace gases. All these molecules float freely, constantly moving and colliding with each other due to thermal motion. And crucially, These molecules are much smaller than the wavelengths of visible light. This size difference is the key to Rayleigh scattering. When light encounters an object that is very small compared to its wavelength, the light interacts with that object in a particular way. The oscillating electric field of the light wave causes the electrons in the molecule to oscillate at the same frequency. This makes the molecule behave like a tiny antenna, absorbing energy from the passing light wave and then immediately re-radiating that energy in random directions. This process is called scattering. The efficiency of this scattering process depends strongly on wavelength. Shorter wavelength light, which oscillates faster and carries more energy, makes the molecular electrons oscillate more vigorously. This leads to more efficient re-radiation. The mathematical relationship, worked out by Lord Rayleigh in 1871, shows that scattering efficiency is inversely proportional to the fourth power of wavelength. This means if you halve the wavelength, the scattering increases by a factor of 16. Let us put numbers to this. Blue light with a wavelength of 400 nanometers scatters much more efficiently than red light with a wavelength of 700 nanometers. The ratio of wavelengths is 700 divided by 400, which equals 1.75. The fourth power of 1.75 is approximately 9.38. So red light experiences about 9.4 times less scattering than blue light when passing through air. This strong wavelength dependence is why Rayleigh scattering preferentially removes short wavelength light from the forward traveling beam of sunlight and redirects it in other directions. When sunlight enters the atmosphere from above, blue and violet photons scatter much more readily than red and orange photons. These scattered blue and violet photons bounce around the atmosphere, coming at your eyes from all directions across the sky. The red and orange photons largely continue straight through with minimal scattering, which is why when you look directly at the sun through significant atmosphere, particularly at sunrise or sunset, the sun itself appears yellow, orange, or red rather than white. But here is the crucial point that the simple Rayleigh scattering explanation misses. If Rayleigh scattering were the only factor, and if the sun produced equal amounts of every wavelength, the sky would appear violet, not blue. Violet light has a wavelength around 400 nanometers compared to blue light around 470 nanometers. The scattering ratio between these two wavelengths means violet should scatter noticeably more than blue. So why do we see blue? This question leads us deeper into the physics and biology of sky color. But before we can answer it, we need to understand Earth's atmosphere in more detail, because the atmosphere is where all the relevant physics takes place. The atmosphere is the gaseous envelope surrounding Earth, held in place by gravity. It extends from the planet's surface upward to altitudes where it gradually fades into the vacuum of space. There is no sharp boundary where atmosphere ends and space begins. Instead, the density of gas molecules decreases continuously with altitude until it becomes effectively indistinguishable from the incredibly sparse matter of interplanetary space. For our purposes, the lowest layer of the atmosphere is most important. This layer is called the troposphere, and it extends from sea level up to roughly 10 to 15 kilometers depending on latitude and weather conditions. The troposphere contains approximately 75 to 80% of the atmosphere's total mass, and this is where weather occurs, where clouds form, and where most of the scattering and absorption of sunlight takes place. The composition of the troposphere is relatively consistent. Dry air at sea level consists of roughly 78% nitrogen molecules, 21% oxygen molecules, and about 1% argon atoms, with trace amounts of carbon dioxide, neon, helium, methane, and other gases. Water vapor varies considerably depending on temperature and location, but typically comprises between 0 and 4% of the atmosphere by volume. These percentages describe the number of molecules of each type, not the mass. Since different molecules have different masses, the mass percentages differ slightly from the volume percentages. But for understanding light scattering, what matters is the number of molecules per unit volume, because each molecule can potentially scatter light regardless of its mass. At sea level, on an average day, each cubic centimeter of Air contains approximately 2.5 times 10 to the power of 19 molecules. Written out, that is 25 billion molecules in a space the size of a sugar cube. This enormous number density means that light traveling through the atmosphere encounters countless molecules as it passes through. Even though each individual molecule is tiny and the probability of any single photon interacting with any single molecule is extremely small, the sheer number of molecules ensures that significant scattering occurs over distances of many kilometers. Nitrogen molecules consist of two nitrogen atoms bonded together, written chemically as N2. Oxygen molecules similarly consist of two oxygen atoms bonded together, written as O2. These molecules are remarkably small. An oxygen molecule measures approximately 0.1 nanometers across. A nitrogen molecule is only slightly larger. Compare this to visible light wavelengths, which range from 380 to 750 nanometers. The ratio means that molecules are roughly 4,000 to 7,000 times smaller than the wavelengths of light they scatter. This size ratio is critical. Rayleigh scattering specifically describes the interaction between electromagnetic radiation and particles that are much smaller than the wavelength of that radiation. If the particles were comparable in size to the wavelength, different scattering physics would apply, a regime described by me scattering theory. If the particles were much larger than the wavelength, yet different physics would apply. But in our atmosphere, for visible light encountering nitrogen and oxygen molecules, we are firmly in the Rayleigh scattering regime. When a photon of light encounters an air molecule, the oscillating electric field of the light wave acts on the electrons in the molecule. Electrons are negatively charged particles, and they respond to electric fields by experiencing force and acceleration. As the electric field oscillates, the electrons in the molecule oscillate along with it, moving back and forth at the same frequency as the light wave. This electron oscillation has an important consequence. According to electromagnetic theory worked out by James Clerk Maxwell in 1865, any accelerating charged particle radiates electromagnetic energy. So the oscillating electrons in the molecule radiate light. They essentially act as tiny antennas, absorbing energy from the incoming light wave and immediately re-radiating it in various directions. From the perspective of the photon, it has encountered the molecule and been deflected onto a new path. Its wavelength and energy remain unchanged in this process, but its direction of travel changes. This is elastic scattering, meaning energy is conserved. The photon loses no energy in the interaction, though it may transfer some momentum to the molecule, causing the molecule to recoil slightly. The probability of this scattering occurring and the angular distribution of the scattered light depend on the wavelength of the light and the properties of the molecule. Lord Rayleigh's mathematical analysis in 1871 showed that for small particles in the Rayleigh scattering regime, the intensity of scattered light is proportional to the fourth power of the frequency, or equivalently, inversely proportional to the fourth power of wavelength. This inverse fourth power law means that small changes in wavelength lead to large changes in scattering intensity. Going from red light at 700 nanometers to blue light at 400 nanometers represents a wavelength decrease by a factor of 1.75, but the scattering increases by a factor of about 9.4. Going from blue at 400 nanometers to violet at 380 nanometers increases scattering by roughly another 30%. Now consider what happens when sunlight enters Earth's atmosphere from above. The beam contains photons of all visible wavelengths mixed together, along with ultraviolet and infrared photons. As the beam travels downward through increasingly dense air, it constantly encounters molecules. Some photons scatter, being deflected onto new paths. Other photons continue forward unscattered. Because shorter wavelength photons scatter more efficiently, they are preferentially removed from the forward traveling beam. After the light has traveled through some thickness of atmosphere, the beam contains proportionally less blue and violet light than it started with, and proportionally more red and orange light. The missing short wavelength photons have scattered away in various directions, bouncing between molecules multiple times in some cases, eventually traveling in directions that have no correlation with the original downward direction of the beam. When you stand on Earth's surface and look up at the sky away from the sun, the light entering your eyes consists mostly of these scattered photons. They originated in the sun, but they have bounced off air molecules one or more times before reaching you. Because blue and violet photons scatter more efficiently than red photons, more blue and violet photons arrive at your eyes from directions away from the sun. This is why the sky appears blue rather than black. You are seeing scattered sunlight, and that scattered sunlight is enriched in short wavelengths due to the wavelength-dependent efficiency of Rayleigh scattering. But we still have not explained why the sky is blue rather than violet. Violet photons scatter even more efficiently than blue photons. So why does the sky not appear violet? The answer requires understanding what happens to light as it travels through progressively more atmosphere, what the sun's radiation spectrum looks like in detail, how ozone absorbs certain wavelengths, and how human eyes respond to different wavelengths. These are the missing pieces that transform the simple Rayleigh scattering story into a complete explanation. John Tyndall, an Irish physicist, performed a series of experiments in 1869 that first revealed the wavelength-dependent nature of light scattering. Tyndall was investigating whether air contained any contaminants that might interfere with his infrared spectroscopy experiments. To test this, he passed bright light through a glass cylinder containing purified air and observed the appearance of the scattered light from the side. What Tyndall noticed was that when very small particles were present in the air, the scattered light appeared blue-tinted. This blue color was faint but unmistakable. Furthermore, when he analyzed the light using a polarizing filter, he found that the scattered light was strongly polarized, with the direction of polarization perpendicular to the direction of the incident light beam. This observation was remarkable because it suggested that scattering from very small particles preferentially affected shorter wavelengths. Tyndall hypothesized that a similar process might explain why Earth's sky appears blue, but he could not develop a mathematical theory to explain the wavelength dependence. He could not explain why blue light scattered more than red light. John William Strutt, who later became the third Baron Rayleigh and is known in physics literature as Lord Rayleigh, developed the mathematical theory in 1871. Rayleigh was working on problems related to the color and polarization of skylight, attempting to quantify the phenomenon Tyndall had observed. His initial papers in 1871 used a simplified model treating scatterers as tiny droplets of water or particles with specific volumes and refractive indices. 10 years later, in 1881, Rayleigh revisited the problem after James Clerk Maxwell had fully developed the electromagnetic theory of light in 1865. Using Maxwell's equations, Rayleigh showed that his earlier results could be derived from fundamental electromagnetic principles. Light consists of oscillating electric and magnetic fields, and when these fields encounter charged particles, specifically electrons in molecules, the fields cause the electrons to oscillate. Oscillating charged particles radiate electromagnetic energy according to Maxwell's theory, and Rayleigh showed that the intensity of this radiation depends on wavelength. Then in 1899, Rayleigh extended his analysis further, showing that the scattering applied not just to particles or droplets, but to individual molecules. This was a significant conceptual leap, because in 1899 the atomic nature of matter was still debated in some quarters. Treating molecules as discrete entities that could scatter light helped establish their physical reality. The key result from Rayleigh's work is the inverse fourth power wavelength dependence. The intensity of scattered light for particles much smaller than the wavelength is proportional to 1 over lambda to the fourth power, where lambda represents wavelength. This can also be written as proportional to frequency to the fourth power, since frequency and wavelength are inversely related. Why the fourth power? The physical explanation goes like this. The oscillating electric field of the light wave causes electrons in the molecule to oscillate. The amplitude of this oscillation, for a given field strength, depends on the frequency. At higher frequencies, the field oscillates faster and the electrons oscillate faster. The acceleration of the electrons, which determines how much electromagnetic energy they radiate, is proportional to the square of the frequency. The power radiated by an oscillating charge is proportional to the square of its acceleration, giving another factor of frequency squared. Multiplying these together gives frequency to the fourth power, or equivalently wavelength, to the minus fourth power. This fourth power dependence creates dramatic differences in scattering efficiency across the visible spectrum. Consider the ratio between violet light at 380 nanometers and red light at 700 nanometers. The wavelength ratio is 700 divided by 380, which equals roughly 1.84. The fourth power of 1.84 is approximately 11.5, so red light scatters about 11.5 times less efficiently than violet light. Blue light at 470 nanometers scatters less efficiently than violet, but more efficiently than red. The wavelength ratio between red at 700 nanometers and blue at 470 nanometers is 700 divided by 470, which equals approximately 1.49. The fourth power of 1.49 is about 4.94. So red light scatters roughly 5 times less efficiently than blue light. These numbers mean that when sunlight passes through Earth's atmosphere, short wavelength photons scatter away from the direct beam much more readily than long wavelength photons. After traveling through significant atmosphere, the beam is depleted in blue and violet light and enriched in red and orange light. This selective removal of short wavelengths is called bulk attenuation, and it becomes particularly important for understanding sunsets, which we will discuss later. The scattered photons, meanwhile, travel in new directions. When you stand on Earth's surface during the day and look at the sky away from the sun, you are looking at scattered photons. These photons originated in the sun, traveled toward Earth, encountered air molecules somewhere in the atmosphere above and around you, scattered onto new paths, and eventually entered your eyes. Because scattering efficiency is so much higher for short wavelengths, many more blue and violet photons arrive at your eyes via scattering than red and orange photons. The photons entering your eyes from the daytime sky are disproportionately short wavelength photons. This is why the sky appears blue instead of appearing the same color as the sun. If you could somehow turn off Rayleigh scattering, the sky would appear black even during the day, because photons would travel straight from the sun to the ground without scattering sideways into your eyes. You would see a black sky with a brilliant white sun, similar to what astronauts see when they look up from the airless surface of the moon. The only reason the sky appears bright during the day is because of scattering, and the only reason it appears blue is because of the strong wavelength dependence of Rayleigh scattering. But Rayleigh scattering, by itself, predicts too much violet in the sky. The inverse fourth power law says violet should scatter more than blue, yet we see blue sky, not violet sky. This is the puzzle we must solve, and solving it requires bringing in the other factors that influence sky color. The first factor is the sun's spectrum. The second is bulk attenuation. The third is ozone absorption. And the fourth is human eye sensitivity. Let us examine each in turn. If you perform a simple thought experiment, the violet sky problem becomes clear. Imagine the sun produces equal amounts of every visible wavelength. Imagine the atmosphere scatters light according to the inverse fourth power law with no other effects. And imagine human eyes respond equally to all visible wavelengths. Under these conditions, when you look at the scattered light from the sky, you would see more violet than blue, more blue than green, and progressively less of the longer wavelengths. The sky would appear violet, possibly with a whitish tint from the mixture of all scattered wavelengths, but distinctly shifted toward the shortest visible wavelengths. This is not what we observe. The sky appears blue, not violet, so at least one of our assumptions must be wrong. It turns out all three assumptions are wrong, and each factor contributes to shifting the perceived color from violet toward blue. Let us start with the sun's spectrum. The sun is not a perfect white light source. It does not produce equal amounts of every wavelength. Instead, as we discussed earlier, the sun's emission follows a thermal blackbody spectrum determined by its surface temperature of approximately 5,500 degrees Celsius. For a blackbody at this temperature, the peak emission occurs around 500 nanometers in the green-yellow region of the spectrum. But the spectrum does not fall to zero outside this peak. Instead, it forms a broad curve that extends across all visible wavelengths and beyond. Crucially, the intensity decreases as you move away from the peak in either direction. At the violet end of the spectrum, around 380 to 400 nanometers, the sun produces significantly less light than at the blue end, around 450 to 500 nanometers. The exact ratio depends on the specific wavelengths you compare, but the sun produces roughly 30 to 40% less violet light than blue light simply because of its thermal spectrum. This reduced violet output means that even though violet light scatters more efficiently than blue light, there are fewer violet photons to scatter in the first place. When you multiply the number of photons at each wavelength by the scattering efficiency at that wavelength, the peak of the scattered light spectrum shifts away from violet and toward blue. But the sun's spectrum alone does not fully explain why we see blue sky instead of violet sky. We need the second factor, which is bulk attenuation. Bulk attenuation describes what happens to the direct beam of sunlight as it travels through progressively more atmosphere. Remember that Rayleigh scattering removes short wavelength photons from the forward traveling beam and redirects them in other directions. As the beam travels downward through the atmosphere, more and more of the short wavelength photons scatter away. The beam becomes progressively depleted in blue and violet light. Now consider what this means for the sky color you observe. When you look up at the sky, you see scattered light. This scattered light comes from all altitudes, from the top of the atmosphere down to just above your head. But different altitudes contribute differently to the final color you perceive. Near the top of the atmosphere, the incoming sunlight still contains plenty of violet and blue photons. Scattering at high altitudes produces violet-blue scattered light. But near the bottom of the atmosphere, after the sunlight has already passed through kilometers of air, much of the violet light has already scattered away. The beam reaching the lower atmosphere is relatively depleted in violet compared to blue. When scattering occurs in the lower atmosphere, blue light scatters more readily than violet, simply because there is more blue light left in the beam. Since the lower atmosphere contains more air molecules than the upper atmosphere due to compression under gravity, more total scattering occurs in the lower atmosphere than in the upper atmosphere. The scattered light that reaches your eyes comes disproportionately from lower altitudes, where the beam has already lost much of its violet content. This shifts the perceived color of the sky toward blue. Bulk attenuation also explains why sunsets are red. At sunset, sunlight must travel through much more atmosphere to reach you because it approaches from a low angle rather than from overhead. The path length through atmosphere might be 30 or 40 times longer at sunset compared to noon. Over this extended path, essentially all the violet and blue photons scatter away. By the time the beam reaches the lower atmosphere, where you can see it, only the long wavelength red and orange photons remain. This is why the setting sun appears red or orange, and why the sky near the horizon at sunset shows red and orange colors. The third factor is ozone absorption. This contribution was discovered by Edward Hurlbut in 1953, and it reveals that scattering is not the only atmospheric process affecting sky color. Ozone molecules, consisting of 3 oxygen atoms bonded together and written chemically as O3, absorb light in specific wavelength ranges. Ozone is most famous for absorbing ultraviolet light, which protects life on Earth's surface from dangerous UV radiation. But ozone also absorbs in the visible spectrum, particularly in the yellow, orange, and red wavelengths. These absorption features are called the Chapuis bands, and they peak around 600 nanometers right in the orange region of the spectrum. When sunlight travels through the atmosphere, ozone molecules absorb some of the orange and red photons. This removal of long wavelength light from the beam means that the scattered light reaching your eyes contains proportionally less orange and red than it otherwise would. The effect is to shift the color balance toward blue. Hurlbut's calculations showed that for certain viewing geometries, particularly when looking at the zenith during sunset, ozone absorption contributes about 2/3 of the blue color, with Rayleigh scattering contributing only about 1/3. This was a surprising result. For decades, scientists had assumed Rayleigh scattering was the complete explanation for blue sky. Hulbert showed that, at least under some conditions, ozone absorption is actually more important than scattering. More recent research has confirmed and extended Hulbert's findings. During the day when the sun is high in the sky, ozone's contribution is relatively minor, perhaps 10 to 20% of the total blue color. But as the sun approaches the horizon, ozone's contribution increases dramatically because the light must travel through more atmosphere and therefore encounter more ozone molecules. At sunset, ozone absorption in the Chapuis bands removes so much orange and red light that the scattered light appears distinctly more blue than it would from Rayleigh scattering alone. The fourth and final factor is human eye sensitivity. This is perhaps the most surprising piece of the puzzle because it reveals that the color of the sky is not purely a physical phenomenon. It also depends on biology. Human eyes do not respond equally to all visible wavelengths. We have 3 types of color-sensing cells in our retinas, called cone cells, and each type responds most strongly to a different range of wavelengths. These are conventionally labeled S cones for short wavelength, M cones for medium wavelength, and L cones for long wavelength, though they are often informally called blue, green, and red cones. The S cones have peak sensitivity around 420 to 440 nanometers in the blue-violet region. The M cones peak around 530 to 540 nanometers in the green region. The L cones peak around 560 to 580 nanometers in the yellow-green region. Note that none of the cones peak in the red region. The perception of red color comes from the L cones being stimulated, while the M cones and S cones are relatively unstimulated, and the brain interprets this pattern as red. The key point is that our eyes are not very sensitive to violet light, around 380 to 400 nanometers. The S cones do respond to violet, but their response is weaker than their response to blue, around 440 nanometers. Additionally, the lens and cornea of the eye absorb some violet and ultraviolet light before it reaches the retina. This provides protection against potential damage from high-energy short-wavelength photons, but it also reduces our sensitivity to violet. So even if the atmosphere scatters plenty of violet light, and that violet light reaches your eyes do not respond to it as strongly as they respond to blue light. The cone cells fire more action potentials in response to blue light than to an equal intensity of violet light, and the brain interprets this neural activity as blue color. When you combine all 4 factors together, the complete picture emerges. The sun produces less violet than blue due to its thermal spectrum. Bulk attenuation preferentially removes violet from the lower atmosphere where most scattering into your eyes occurs. Ozone absorption removes orange and red light, shifting the color balance further toward blue. And human eyes respond more strongly to blue than to violet. Each factor shifts the perceived color away from violet and toward blue. Together, they explain why the sky appears blue instead of violet. This is the answer most people never learn. The sky is blue not just because of Rayleigh scattering, but because of the combination of Rayleigh scattering, solar spectrum characteristics, bulk attenuation, ozone absorption, and human visual sensitivity. Remove any one of these factors and the sky would appear a different color. They all work together to produce the specific shade of blue you see when you look up on a clear day. Ozone deserves special attention because its contribution to sky color remained unrecognized for decades after Rayleigh scattering was understood. Edward Olson Hulbert, working at the U.S. Naval Research Laboratory, published his findings in 1953 in a paper titled Explanation of the Brightness and Color of the Sky, particularly the Twilight Sky. This paper demonstrated that previous explanations of sky color were incomplete. Hulbert's work focused particularly on twilight, the period after sunset when the sun is below the horizon, but the sky is still illuminated. During twilight, the geometry of light propagation becomes more complex. Sunlight must travel through the atmosphere at very low angles, passing through enormous amounts of air before scattering toward an observer. This creates conditions where subtle atmospheric effects become magnified and visible. Hulbert performed calculations using simplified radiative transfer models and single scattering approximation. He considered what color the zenith sky should appear during sunset, when the sun is exactly on the horizon. His calculations included both Rayleigh scattering and the absorption of light by ozone in the Chapuis bands. The Chapuis bands span roughly 450 to 750 nanometers, covering most of the visible spectrum, but they are strongest in the yellow-orange-red region between 500 and 650 nanometers. When sunlight passes through ozone, these wavelengths are preferentially absorbed. The absorption is not complete, meaning some yellow, orange, and red light still gets through, but the proportions are reduced compared to the blue and green wavelengths. Hulbert's key finding was quantitative. For the specific case of looking at the zenith when the sun is on the horizon, he calculated that Rayleigh scattering contributed approximately 1/3 of the blue color, while ozone absorption contributed approximately 2/3. This meant that ozone was twice as important as Rayleigh scattering for producing the blue color under those specific conditions. This result challenges the simple explanation most people are taught. Scattering is often presented as the sole cause of blue sky, but Hulbert showed that absorption is equally important, and under some conditions more important. The sky appears blue partly because blue light scatters efficiently, but also partly because red and orange light are absorbed by ozone, leaving more blue in the remaining light. For many years, Hulbert's paper received relatively little attention. The scientific community had accepted Rayleigh scattering as the explanation for blue sky, and there seemed little reason to revisit the question. But in recent years, researchers have returned to Hulbert's work and verified his conclusions using modern computational methods. A 2023 study published in the journal Atmospheric Chemistry and Physics used sophisticated radiative transfer models to recalculate the contribution of ozone to sky color across different viewing geometries and solar positions. The researchers confirmed Hulbert's estimate with remarkable accuracy. For the sun on the horizon and viewing angle at the zenith, ozone absorption accounts for roughly 2/3 of the blue color, just as Hulbert calculated 70 years earlier using much simpler methods. The same study extended the analysis to other viewing geometries. When the sun is high in the sky, ozone's contribution diminishes. During midday, when the sun is overhead, or nearly so, Rayleigh scattering dominates and ozone absorption contributes perhaps only 10 to 20% of the blue color. But as the sun approaches the horizon, ozone's importance increases. The reason is simple geometry. Low sun angles mean light must travel through more atmosphere, encountering more ozone molecules. Each ozone molecule absorbs a small fraction of the passing orange and red photons. Over long path lengths through the atmosphere, this absorption becomes significant. The research also showed that the total ozone column, meaning the total amount of ozone in the atmosphere above a given location, affects the perceived blue color. Locations with higher ozone concentrations show slightly deeper blue skies during twilight. Locations with lower ozone show slightly less blue. This effect is small during midday, but becomes more noticeable at sunrise and sunset. Volcanic eruptions can also affect the ozone contribution. Large explosive eruptions inject sulfur dioxide into the stratosphere, which converts to sulfate particles. These particles scatter light, but they also affect ozone chemistry. After major eruptions, the stratosphere contains elevated levels of sulfate particles for months or years. This changes both the scattering and absorption characteristics of the upper atmosphere, potentially brightening the blue color of the sky and enhancing the colors of sunsets and sunrises. Historical records suggest that particularly vivid sunsets occurred in the years following major volcanic eruptions. Some paintings by the artist J.M.W. Turner, who was active in the early 1800s, show intensely red and orange skies that may have been inspired by enhanced sunset colors following the eruption of Mount Tambora in 1815. While we cannot know for certain whether Turner's paintings reflect actual atmospheric conditions, the correlation between major eruptions and enhanced sky colors is well established. Ozone itself is a pale blue gas. If you could collect a large volume of pure ozone at ordinary temperatures and pressures, it would appear blue. In the stratosphere, where most atmospheric ozone resides, temperatures are very low, and if liquid ozone could exist at those temperatures, it would likely appear deep blue. But the amount of ozone in the atmosphere is quite small. Even in the ozone layer, which peaks at altitudes around 25 to 30 kilometers, ozone comprises only a few parts per million of the total atmosphere. The ozone layer is not blue for the same reason the sky is blue. The blue color of the sky comes from scattering and absorption affecting sunlight, not from any intrinsic color of the atmospheric gases themselves. Other planets with different atmospheric compositions show different sky colors, which highlights the importance of atmospheric chemistry to sky color. Mars, for example, has a very thin atmosphere composed mostly of carbon dioxide with no significant ozone layer. The Martian daytime sky appears butterscotch or peachy orange rather than blue, though there is a blue tint near the sun at sunset due to scattering from atmospheric dust particles. Venus has a thick atmosphere, mostly of carbon dioxide with sulfuric acid clouds. The surface of Venus, when photographed by landers, shows an orangish or yellowish sky due to the filtering effects of the thick atmosphere and clouds. Earth's blue sky is thus partly a consequence of having an oxygen-rich atmosphere with an ozone layer. The oxygen comes from photosynthesis by plants and photosynthetic bacteria over billions of years. The ozone forms when ultraviolet light splits oxygen molecules, and the resulting oxygen atoms combine with other oxygen molecules. Without life producing oxygen, Earth's atmosphere would not contain ozone, and the sky would appear somewhat different, though Rayleigh scattering alone would still produce a blue tint. The ozone contribution to blue sky is a reminder that, seemingly, simple phenomena often have multiple contributing causes. When generations of people are taught that the sky is blue because of Rayleigh scattering, they receive a true but incomplete explanation. The complete explanation requires also considering ozone absorption, along with the solar spectrum, bulk attenuation, and human eye sensitivity. Only by assembling all these pieces can we truly understand why the sky appears the particular shade of blue that it does. Color does not exist in the external world. This is a strange statement because we experience color as a fundamental property of objects. The sky is blue, grass is green, roses are red. These seem like facts about the world. But in reality, color is a creation of the brain, an interpretation of electromagnetic radiation at different wavelengths. Light has wavelength. Objects reflect or emit certain wavelengths preferentially. But wavelength is just a physical property, a number measured in nanometers. The conversion of wavelength into the subjective experience of color happens in the retina and brain. Different wavelengths trigger different neural responses, and those neural responses are interpreted as different colors. But the mapping from wavelength to color is not inevitable or universal. It is specific to the structure of human visual systems. Human color vision depends on 3 types of cone cells in the retina. Each type contains a different photopigment protein that responds most strongly to a particular range of wavelengths. The S cones, short wavelength cones, contain a photopigment that peaks in sensitivity around 420 nanometers in the blue-violet region. The M cones, medium wavelength cones, contain a photopigment that peaks around 530 nanometers in the green region. And the L cones, long wavelength cones, contain a photopigment that peaks around 560 to 570 nanometers in the yellow-green region. These peak sensitivities do not mean the cones only respond to those specific wavelengths. Each cone type responds to a broad range of wavelengths, with sensitivity falling off gradually on either side of the peak. The S cones respond to light from about 400 to 500 nanometers. The M cones respond from about 450 to 650 nanometers. The L cones respond from about 500 to 700 nanometers. There is substantial overlap between the sensitivity ranges. When light enters the eye and reaches the retina, photons are absorbed by the photopigment molecules in the cone cells. This absorption triggers a molecular change in the photopigment, which initiates a cascade of biochemical reactions inside the cell, eventually causing the cell to send an electrical signal to the brain via neurons. The rate at which this signal is sent encodes the intensity of light at the wavelengths the cell is sensitive to. The brain receives signals from all three cone types simultaneously. By comparing the relative strengths of these signals, the brain can distinguish different wavelengths of light. If the S cones are strongly activated while M cones and L cones are weakly activated, the brain interprets this as blue or violet. If M cones are strongly activated while S cones and L cones are moderately activated, the brain interprets this as green. If L cones are strongly activated while M cones are moderately activated and S cones are weakly activated, the brain interprets this as red. This system allows humans to distinguish roughly 10 million different color shades, despite having only 3 cone types. The key is that the brain is comparing ratios between cone signals, not just absolute signal strengths. Different combinations of the 3 signals produce different perceived colors. For our purposes, the critical point is that human eyes do not respond equally to all visible wavelengths. Consider violet light at 380 nanometers versus blue light at 460 nanometers. Both wavelengths activate the S cones, but the S cones are more sensitive to 460 nanometers than to 380 nanometers. The S cone sensitivity curve peaks around 420 nanometers and falls off on both sides, being lower at 380 and lower at 460, but still higher at 460 than at 380. Additionally, the cornea and lens absorb short wavelength light, particularly ultraviolet and deep violet wavelengths. This absorption serves a protective function, preventing high-energy photons from damaging the retina. But it also means that violet light around 380 to 400 nanometers is partially filtered out before it reaches the cone cells. Less violet light reaches the retina compared to blue light, even if equal amounts of violet and blue light enter the eye. The combined effect is that the human visual system is less sensitive to violet than to blue. If the sky scattered equal amounts of violet and blue light, the sky would appear more blue than violet to our eyes, simply because we respond more strongly to blue. Some people have better violet sensitivity than others due to individual variations in eye structure and photopigment properties. People who have had cataract surgery and have had their natural lens replaced with an artificial lens that does not absorb violet light sometimes report being able to see violet colors more vividly. The famous artist Claude Monet reportedly experienced this after cataract surgery late in his life, and his paintings from that period show enhanced blue and violet tones, possibly reflecting his altered color perception. Color perception also varies with light intensity. The cone cells function best in daylight conditions. In very low light, the cone cells become less sensitive, and vision is taken over by rod cells, which are more sensitive to light but cannot distinguish colors. Rods have peak sensitivity around 500 nanometers in the blue-green region. This shift in sensitivity as light dims is called the Purkinje effect, and it explains why blue and green objects appear relatively brighter than red objects in low light. In full moonlight, the sky technically appears blue for the same reason it appears blue in sunlight, because moonlight is reflected sunlight and undergoes the same Rayleigh scattering in the atmosphere. But most people do not perceive the moonlit sky as blue because light levels are low enough that color vision from cones is suppressed and rod cells dominate. The rods signal that the sky is bright, but they do not distinguish color, so the brain perceives the moonlit sky as grayish-white rather than blue. Individual variation in color perception extends beyond violet sensitivity. People with color vision deficiencies, commonly called color blindness, have missing or altered cone types and perceive colors differently. The most common form, called red-green color blindness, affects the L cones or M cones and makes it difficult to distinguish reds, oranges, yellows, and greens. People with this condition can still see the sky as blue because the S cones are unaffected, but their overall color perception differs from typical trichromatic vision. Some rare individuals have 4 types of cone cells instead of 3, a condition called tetrachromacy. These people, almost always women due to the genetic mechanism involved, can potentially distinguish colors that look identical to people with normal trichromatic vision. For tetrachromats, the sky might appear subtly different than it does for the rest of us, though describing that difference is challenging because we lack the vocabulary for colors that trichromats cannot see. The relationship between wavelength and perceived color is also nonlinear. Small changes in wavelength at some parts of the spectrum produce large changes in perceived color, while equivalent wavelength changes at other parts produce barely noticeable differences. Humans are particularly sensitive to wavelength differences in the blue, green, and yellow regions, where the sensitivity curves of the cone types overlap most strongly. We are less sensitive to wavelength differences in the deep blue or deep red regions. All of this means that the blue sky is, in a very real sense, a collaboration between physics and biology. The physics of Rayleigh scattering, solar radiation spectrum, atmospheric path length, and ozone absorption determine what wavelengths of light reach your eyes. But the biology of cone cells, photopigments, neural processing, and brain interpretation determines what color you consciously perceive. Change either the physics or the biology, and the perceived color would change. If humans had cone cells that peaked at different wavelengths, the sky might appear a different color even, though the physics remained identical. If our most sensitive cone peaked at 400 nanometers instead of 420, we might perceive the sky as more violet. If it peaked at 500 nanometers, we might perceive the sky as more cyan or greenish. The specific blue we see is determined by the overlap between the physical spectrum of scattered light and the biological response curves of our cone cells. This realization has implications beyond understanding sky color. It reveals that much of what we consider objective reality is actually a construct of our sensory systems and brains. Color is the most obvious example, but the same principle applies to other perceptions. Sound is our interpretation of pressure waves in air. Smell is our interpretation of specific molecules binding to receptors in our nose. Temperature is our interpretation of molecular kinetic energy. The world as we experience it is not the world as it exists independently of observers. It is a model constructed by our brains from limited sensory data. None of this makes color any less real or meaningful. The blue sky exists as a shared perceptual experience for humans. We all see roughly the same blue when we look up, with minor individual variations. The physics of light scattering and absorption is objective and measurable. But the connection between those physics and the subjective experience of blueness requires the biology of human vision. Both are necessary. Neither is sufficient alone. Other animals with different visual systems see the sky differently. Many birds have 4 types of cone cells, including one sensitive to ultraviolet wavelengths. Birds likely see more violet and ultraviolet in the sky than humans do. Some insects also have ultraviolet sensitivity. Honeybees, for example, have 3 types of photoreceptors with peak sensitivities at 340 nanometers in ultraviolet, 430 nanometers in blue, and 540 nanometers in green. To a bee, the sky appears different than it does to a human, probably richer in violet tones extending into wavelengths we cannot see. Dogs and many other mammals have only 2 types of cone cells, making them dichromats rather than trichromats like most humans. Their color vision is roughly similar to human red-green color blindness. Dogs can see blue and yellow but cannot distinguish reds and greens well. To a dog, the sky still appears blue because their short wavelength cones respond to blue light, but the overall richness of their color experience differs from ours. Marine mammals like dolphins and whales have lost color vision entirely in many cases, having only a single cone type or sometimes only rod cells. This makes sense for animals living in ocean depths where little light penetrates. Color vision provides little advantage in near darkness, so evolution has eliminated the extra cone types. These animals see the world in shades of gray. 2a. Dolphin. Looking up at the surface from underwater, The sky appears as varying brightnesses, but not as colors. The evolution of color vision in humans and other primates is thought to relate to identifying ripe fruits. Fruits ripen and change color, often from green to red, orange, or yellow. Being able to distinguish these color changes provides an advantage for finding food. Our three cone types, with peaks in the blue, green, and yellow-green regions, are well suited to distinguishing the yellows, oranges, and reds of ripe fruits against the green background of leaves. The same visual system that helps us find ripe mangoes also allows us to perceive blue sky. This evolutionary history means that the sky's blue is meaningful to us, partly because we evolved to be sensitive to it. If color vision had evolved for different purposes, our cone types might peak at different wavelengths, and the sky might look different to us even though the physics remained unchanged. The blue sky exists at the intersection of stellar physics, atmospheric physics, and evolutionary biology. All three shaped what we see when we look up. Sunset is daytime sky physics pushed to its extreme. When the sun sits low on the horizon at dawn or dusk, light must travel through far more atmosphere to reach you than it does at noon when the sun is overhead. This extended path length amplifies all the atmospheric effects we have discussed, transforming the brilliant blue of midday into the reds, oranges, and pinks of sunset and sunrise. The geometry is straightforward. When the sun is directly overhead, sunlight enters the atmosphere from above and travels downward to the surface. The path length through atmosphere is minimal, perhaps 100 kilometers if we define the top of the atmosphere loosely. When the sun is on the horizon, sunlight enters the atmosphere at a shallow angle. It must traverse the atmosphere horizontally or nearly so, passing through far more air before reaching the surface. The exact path length depends on atmospheric structure, refraction effects, and the observer's altitude, but a typical value is approximately 38 times longer than the overhead path. This factor of 38 makes an enormous difference. Recall that Rayleigh scattering removes short wavelength light from the direct beam. Each kilometer of atmosphere removes a certain fraction of blue and violet light. After 1 kilometer, perhaps a small percentage has scattered away. After 10 kilometers, more has scattered. After 100 kilometers, a substantial fraction has scattered. After 38 times 100 kilometers, nearly all of it has scattered. The same inverse fourth power wavelength dependence that causes blue sky causes red sunsets. Blue light, with its wavelength of approximately 470 nanometers, scatters about 5 times more efficiently than red light at 700 nanometers. This means blue light is removed from the beam about 5 times faster per unit distance traveled. Over the long horizontal path through atmosphere at sunset, blue light scatters away almost completely, leaving primarily red, orange, and yellow wavelengths in the direct beam. When you look at the setting sun, you are looking directly at this depleted beam. The sun appears red or orange because most of the blue has been removed. The same light that makes the sky blue during the day causes the sun to appear red at sunset. The blue photons have scattered away and are illuminating the sky elsewhere, while the red photons continue straight through to your eyes. The amount of atmosphere matters. On days when the atmosphere is very clear, with few particles suspended in it, the setting sun appears deep red or burgundy. The Rayleigh scattering from molecules alone is enough to remove most blue light, but allows red and deep orange to pass through. On days when the atmosphere contains more particles from dust, pollen, or pollution, the setting sun may appear lighter orange or even yellowish orange because particles scatter light somewhat differently than molecules do, removing less blue but also removing some red. Volcanic eruptions can produce spectacular sunsets by injecting fine ash and sulfur dioxide into the stratosphere. The sulfur dioxide converts to tiny sulfate droplets that remain suspended for months or years. These droplets scatter light in ways that enhance red and orange colors while maintaining some scattering of yellow and green. The result is intensely colorful sunsets with deep reds transitioning to oranges and yellows, often extending far across the sky. The 1991 eruption of Mount Pinatubo in the Philippines produced notable sunset effects for several years afterward. The eruption injected approximately 20 million tons of sulfur dioxide into the stratosphere. Observers worldwide reported unusually vivid sunsets, with reds appearing deeper and the colorful zone extending higher above the horizon. Satellite measurements confirmed increased aerosol content in the stratosphere that gradually declined over the following 3 to 4 years as the particles settled or were removed by atmospheric processes. Historical records suggest that the 1883 eruption of Krakatoa in Indonesia produced even more dramatic effects. Descriptions from that era mention blood-red sunsets visible in Europe and North America months after the eruption. Some paintings from that period show remarkably lurid sunset colors that may reflect actual atmospheric conditions. The artist Edvard Munch's famous painting, The Scream, shows a vivid red-orange sky that some researchers believe may have been inspired by Krakatoa-enhanced sunsets, though this interpretation remains debated. Besides the direct beam of sunlight showing red or orange when the sun is near the horizon, the sky surrounding the sun also shows colors during sunset. These colors grade from orange nearest the sun through yellow to blue higher up in the sky. This gradation reflects the continuous change in path length and scattering conditions as you look at different angles. When you look at the horizon near the setting sun, you see light that has traveled through maximum atmosphere, with most blue removed. As your gaze moves upward away from the horizon, you see light that has traveled through progressively less atmosphere, with progressively more blue retained. High overhead, far from the sun, the sky still appears blue even during sunset, because light reaching that part of the sky has traveled a shorter path through atmosphere and retains more blue wavelengths. The time just after sunset, called twilight, produces particularly interesting colors. After the sun drops below the horizon, direct sunlight no longer reaches the surface, but it still illuminates the upper atmosphere. This high-altitude sunlight scatters back down to observers on the ground, creating twilight. The colors depend on how much atmosphere the sunlight must traverse and where the scattering occurs. Civil twilight lasts until the sun is 6 degrees below the horizon. During this period, the horizon appears orange or yellow, fading to blue overhead. Nautical twilight extends until the sun is 12 degrees below the horizon. The horizon darkens to deep orange or purple, and stars become visible overhead. Astronomical twilight continues until the sun is 18 degrees below the horizon, at which point the sky becomes fully dark and faint stars and galaxies become visible even at the zenith. The color sequence during twilight, moving from horizon to zenith, often shows orange transitioning to pink or purple, then to deep blue. These colors reflect light that has scattered multiple times in the upper atmosphere and has traveled through different amounts of ozone. The purple colors are particularly interesting because they occur when red light scattered from the setting sun mixes with blue light scattered from the still illuminated upper atmosphere. At very high altitudes above most of the atmosphere, sunsets look different. Astronauts on the International Space Station, orbiting at approximately 400 kilometers altitude, observe a thin blue line along Earth's limb at sunset. This blue layer is the atmosphere viewed edge-on, with sunlight scattering from the densest parts of the lower atmosphere. Above this blue line, the sky is black even in full sunlight, because there are too few molecules for scattering to occur. The sun appears white rather than yellow because the light has not passed through atmosphere. The thin blue line represents essentially all the atmospheric scattering compressed into a narrow visible band. Moonlight also undergoes scattering and produces a blue sky, at least in principle. The moon has no light of its own, but reflects sunlight. This reflected sunlight, when it enters Earth's atmosphere, scatters just like direct sunlight. However, moonlight is much dimmer than sunlight, roughly 400,000 times dimmer. At these low light levels, human color vision becomes unreliable. Rod cells take over from cone cells, and we perceive mostly brightness rather than color. So even though the physics produces a blue sky, we perceive it as gray or colorless in moonlight. People who have been in very bright moonlight in locations with no other light sources sometimes report seeing subtle blue tints in the sky. This may represent the threshold where light levels are just bright enough for cone cells to function marginally. But for most people most of the time, the moonlit sky appears gray. Total solar eclipses create unusual lighting conditions. During totality, when the moon completely blocks the sun, daylight is replaced by the faint light from the sun's corona and from sunlight scattering in the atmosphere beyond the moon's shadow. Observers report that the sky appears dark blue or purple during totality, with stars visible overhead. This color reflects reduced light levels and altered scattering geometry. Light reaching the observer during totality has scattered from atmosphere outside the shadow region, and the path geometry differs from normal daylight. Partial eclipses also create subtle color shifts. As the moon progressively covers more of the sun, the total amount of sunlight entering the atmosphere decreases, but the scattering physics remains the same. The sky appears slightly deeper blue during partial eclipse because light levels drop, but the proportion of blue light in scattered light stays constant. This effect is subtle and easily overlooked unless you know to watch for it. All these sunset and twilight phenomena demonstrate that sky color is not static. It changes continuously as the sun moves across the sky, as atmospheric conditions vary, as seasons change, and as natural events like volcanic eruptions modify atmospheric composition. The blue sky of midday and the red sunset are not different phenomena, but rather different manifestations of the same underlying physics viewed under different geometric conditions. Understanding sunset helps clarify why the simple Rayleigh scattering explanation of blue sky is incomplete. If Rayleigh scattering were the only relevant process, the math describing blue sky and red sunset would be essentially identical, just evaluated for different path lengths. But as we have discussed, ozone absorption, solar spectrum shape, bulk attenuation, and eye sensitivity all contribute. These factors matter for sunset as well, but in altered ways because the geometry has changed. At sunset, ozone's contribution to blue color becomes particularly important. Remember Edward Hulbert's finding that ozone contributes about 2/3 of the blue color at zenith when the sun is on the horizon. This reflects the long path through atmosphere, which causes the direct beam to encounter many ozone molecules. The Chapuis band absorption removes orange and red wavelengths, shifting the scattered light toward blue. Without ozone absorption, sunset sky colors would shift toward longer wavelengths and appear less saturated. The study of sunset and twilight colors remains an active area of atmospheric optics research. Researchers use sophisticated radiative transfer models to predict sky colors under different conditions and compare these predictions to observations. Satellite measurements of atmospheric composition, aerosol content, ozone distribution, and other parameters feed into these models. The goal is to understand not just average conditions, but also how specific atmospheric events, like dust storms, biomass burning, industrial pollution, and volcanic eruptions affect sky colors. Climate change is gradually altering sky colors in subtle ways. Increasing atmospheric carbon dioxide does not directly affect light scattering because carbon dioxide is transparent to visible light. But climate change affects other atmospheric properties that do matter. Changes in humidity alter the amount of water vapor, which affects scattering. Changes in vegetation and land use patterns affect dust and pollen in the atmosphere. Changes in wildfire frequency increase smoke particles. All these effects combine to shift the colors of sky and sunset in ways that are difficult to predict, but are increasingly being measured and modeled. The next time you watch a sunset, you are witnessing the same physics that explains blue sky, just pushed to an extreme. The red sun demonstrates that blue light has scattered away. The gradation from orange near the horizon to blue overhead demonstrates the continuous change in atmospheric path length. The vivid colors on days after weather fronts clear the atmosphere demonstrate how particles enhance scattering. And the gradual fading of colors as twilight deepens demonstrates how rapidly light levels drop once the direct beam from the sun is cut off. So why is the sky blue? The complete answer integrates everything we have discussed across these past sections. It is not a single phenomenon, but a combination of physical and biological processes that together produce the specific color we perceive when we look upward on a clear day. Start with the sun. The Sun is a ball of plasma with a surface temperature of approximately 5,500 degrees Celsius. At this temperature, it emits electromagnetic radiation across a broad spectrum with peak intensity around 500 nanometers in the green-yellow region. But the spectrum is broad. The Sun produces substantial amounts of violet, blue, green, yellow, orange, and red light, along with ultraviolet and infrared radiation invisible to human eyes. This sunlight travels through the vacuum of space at the speed of light, crossing the approximately 150 million kilometers from the Sun to Earth in about 8 minutes and 20 seconds. During this journey, the light does not change. The photons maintain their wavelengths and travel in straight lines until they encounter Earth's atmosphere. The atmosphere begins gradually at altitudes around 100 kilometers and increases in density toward the surface. In the troposphere, the lowest atmospheric layer extending from the surface to about 10 to 15 kilometers altitude, the air is dense enough that sunlight encounters enormous numbers of molecules. Each cubic centimeter contains approximately 25 billion molecules, mostly nitrogen and oxygen. These molecules are very small, about 0.1 nanometers across, which is thousands of times smaller than visible light wavelengths ranging from 380 to 750 nanometers. This size difference places the interaction firmly in the Rayleigh scattering regime, where scattering efficiency follows an inverse fourth power dependence on wavelength. When a photon of light pulp encounters an air molecule, the oscillating electric field of the light wave causes electrons in the molecule to oscillate. These oscillating electrons radiate electromagnetic energy in random directions, effectively deflecting the photon onto a new path. This process is scattering, and it removes photons from the forward-traveling beam of sunlight and redirects them in other directions. The probability of scattering depends strongly on wavelength. Shorter wavelength light scatters much more efficiently than longer wavelength light. Blue light at 470 nanometers scatters approximately 5 times more efficiently than red light at 700 nanometers. Violet light at 380 nanometers scatters even more efficiently than blue, approximately 30% more. As sunlight travels downward through the atmosphere, short wavelength photons preferentially scatter away from the direct beam. By the time the beam reaches the surface, it has been depleted in blue and violet light. The scattered photons bounce around the atmosphere, many of them eventually traveling downward toward an observer on the ground from directions that have no correlation with the original direction of the beam. When you stand on the surface and look up at the sky away from the Sun, the light entering your eyes consists of these scattered photons. Because short wavelengths scatter more efficiently, more blue and violet photons arrive at your eyes from the sky than red and yellow photons. This is the fundamental reason the sky appears colored rather than black. Without scattering, photons would travel straight from sun to ground, and the sky would appear black even during the day, just as it does on the airless moon. But Rayleigh scattering alone would produce a violet sky, not a blue sky. Violet scatters most efficiently, so you might expect the sky to appear violet. The fact that it appears blue reveals that other factors are modifying the result. The first additional factor is the Sun's spectrum. The Sun does not produce equal amounts of every wavelength. Its thermal blackbody spectrum means it produces less violet light than blue light, roughly 30 to 40% less. So even though violet scatters more efficiently per photon, there are fewer violet photons available to scatter in the first place. This shifts the peak of scattered light away from violet toward blue. The second factor is bulk attenuation. As the direct beam of sunlight travels through atmosphere, blue and violet photons scatter away continuously. Near the top of the atmosphere, the beam still contains plenty of violet and blue, but by the time it reaches lower altitudes, much of the violet has already scattered away. The lower atmosphere, which is denser and therefore produces more total scattering, receives light that is relatively depleted in violet compared to blue. Since lower altitude scattering contributes more to the light reaching your eyes, the perceived color shifts toward blue. The third factor is ozone absorption. Ozone molecules in the stratosphere absorb light in the Chapuis bands, which span the yellow, orange, and red regions of the spectrum. This removes long wavelength photons from both the direct beam and from scattered light. The result is that the scattered light reaching your eyes contains proportionally less red and orange, shifting the color balance further toward blue. During midday, ozone contributes perhaps 10 to 20% of the blue color. At sunset, when light must travel through more atmosphere and encounter more ozone, the contribution rises to about 2/3 of the blue color you perceive overhead. The fourth factor is human eye sensitivity. Your retinas contain 3 types of cone cells with different wavelength sensitivities. These cones peak at approximately 420 nanometers for S cones, 530 nanometers for M cones, and 570 nanometers for L cones. The S cones respond to both violet and blue light, but they respond more strongly to blue around 440 nanometers than to violet around 380 nanometers. Additionally, the cornea and lens of your eye absorb some violet and ultraviolet light before it reaches the retina. This protection mechanism reduces damage from high-energy photons, but also reduces your sensitivity to violet. The combined effect means that even if equal amounts of violet and blue light enter your eye, your visual system responds more strongly to the blue, and your brain interprets the resulting neural activity as blue color. When all 4 factors combine, the result is blue sky. Rayleigh scattering enriches the scattered light in short wavelengths. The solar spectrum provides more blue than violet to begin with. Bulk attenuation preferentially removes violet from lower altitude light. Ozone absorption removes long wavelengths, enhancing the blue proportion. And human eye sensitivity responds more strongly to blue than to violet. Each factor shifts the result in the same direction, from violet toward blue. This is why 99% of people cannot fully explain why the sky is blue. The commonly taught explanation mentions only Rayleigh scattering. That explanation captures the most important single factor, but misses 3 others that are necessary for the complete picture. Without all 4 factors, you cannot explain why the sky is blue instead of violet. You cannot explain why sunset is red. You cannot explain why twilight shows the colors it does. You cannot explain variations in sky color with atmospheric conditions, altitude, or individual differences in visual perception. The complete explanation reveals something profound about scientific knowledge. Simple explanations often capture important truths, but leave out equally important nuances. Teaching that the sky is blue because of Rayleigh scattering is not wrong, but it is incomplete. The completeness matters for deep understanding. It matters for appreciating the elegance of how multiple phenomena combine to produce observable effects. It matters for recognizing that the everyday world around us is more complex and more fascinating than casual observation suggests. This pattern repeats across science. Most phenomena have multiple contributing causes. When you first learn about something, you receive a simplified explanation that captures the main effect. As you learn more, additional factors emerge. Each adds detail and shifts the picture slightly. The complete explanation is almost always more complex than the initial one, but also more satisfying because it accounts for observations that the simple explanation cannot. The sky's blue color is a perfect example. Anyone can look up and see blue. Most people accept a simple explanation without questioning it. But those who dig deeper discover a richer story involving stellar physics, atmospheric physics, molecular chemistry, quantum mechanics, radiative transfer, and neurobiology. The blue you see when you look up is the product of processes occurring across spatial scales from nanometers to millions of kilometers, temporal scales from femtoseconds to billions of years, and conceptual frameworks spanning multiple scientific disciplines. Moreover, the sky's blue is not static. It varies with time of day, season, weather, atmospheric composition, altitude, and individual biology. No 2 people see exactly the same blue because no 2 people have identical visual systems. The sky you see right now is different from the sky you saw yesterday and different from the sky you will see tomorrow. It changes continuously as the sun moves, as clouds form and dissipate, as winds transport air masses, as humidity rises and falls. This variability means that the question, "Why is the sky blue?" does not have a single fixed answer, but rather an answer that depends on specifying conditions. The blue at noon in summer in the mountains differs from the blue at mid-morning in winter at sea level. Both differ from the blue seen from an airplane at cruising altitude. All are explained by the same fundamental physics, but the quantitative details vary with conditions. Scientists continue studying atmospheric optics because applications extend beyond satisfying curiosity about sky color. Understanding light propagation through the atmosphere matters for remote sensing, where satellites measure sunlight reflected from Earth's surface to deduce information about land use, vegetation health, ocean properties, and atmospheric composition. It matters for climate modeling, where accurate treatment of radiative transfer affects predictions of temperature, precipitation, and other climate variables. It matters for astronomy, where ground-based telescopes must correct for atmospheric effects that blur and distort images of distant stars and galaxies. Adaptive optics systems in modern telescopes measure atmospheric turbulence in real time and adjust mirror shapes to counteract it, producing images nearly as sharp as space telescopes. But these systems require understanding exactly how the atmosphere affects light, which connects directly to the same Rayleigh, scattering, and absorption processes that make the sky blue. It matters for aviation and navigation, where understanding visibility conditions helps pilots fly safely. It matters for solar energy, where atmospheric effects reduce the amount of sunlight reaching ground-level solar panels. It matters for agriculture, where the spectrum of light reaching crops affects photosynthesis efficiency. It matters for health, where understanding UV radiation transmission through the atmosphere informs sunscreen recommendations and skin cancer prevention strategies. The sky's blue is thus not just a pretty phenomenon to enjoy during a pleasant afternoon. It is a manifestation of fundamental physics that connects to countless practical applications. By understanding it deeply, we gain insight into how our world works and how to solve problems that depend on atmospheric optics. And, perhaps most importantly, understanding why the sky is blue reveals that even the most ordinary, everyday experiences rest on extraordinary complexity. Nothing is truly simple once you examine it closely. The blue overhead is not just blue. It is Rayleigh, scattering, and solar spectra, and bulk attenuation, and ozone absorption, and cone cell sensitivity, and neural processing, and conscious perception all happening simultaneously. Every instant you spend looking at the sky, these processes unfold at molecular and atomic scales, shaping the light that enters your eyes and the neural signals that reach your brain. This realization applies beyond sky color. Everything you experience is the result of countless processes occurring at multiple scales. The solidity of the ground beneath your feet is electromagnetic forces between atoms. The warmth of sunlight on your skin is infrared photons transferring energy to your molecules. The flavor of food is molecules binding to receptors and triggering neural signals. The thought you are having right now is electrochemical activity across networks of neurons. Reality is not simple. It is staggeringly complex. But that complexity follows understandable principles. Physics, chemistry, and biology combine to create the world you inhabit. The same rules that explain blue sky also explain sunsets, rainbows, mirages, auroras, and countless other atmospheric optical phenomena. They explain how stars produce light, how that light travels through space, how planets form atmospheres, how life evolves visual systems to detect light, and how conscious beings interpret sensory data to form perceptions. The question, why is the sky blue, opens a window onto this vast, interconnected web of knowledge. The answer requires understanding stars, atmospheres, molecules, photons, cells, and brains. It requires mathematics to describe scattering, chemistry to understand ozone, biology to explain vision, and physics to tie it all together. And, having assembled this understanding, you now possess something valuable. You understand not just a fact about the world, but how multiple layers of reality combine to produce observable phenomena. You understand why the simple answer falls short. You understand what factors the simple answer omits. You understand how to think about complex phenomena that resist simple explanation. And you understand that the universe rewards curiosity with deeper insight with more comprehensive understanding, with revelations that transform the familiar into the extraordinary. The sky is blue for reasons that span from the quantum mechanical behavior of electrons in molecules to the evolutionary history that shaped human vision. That is the complete answer. That is what 99% of people never learn. And now you know it. The sky has not changed as we have moved through this exploration. It was blue when we began, and it remains blue now. But perhaps your perception of that blue has changed. What appeared simple and obvious at the start now reveals itself as the product of multiple causes operating simultaneously at different scales. The blue is still just blue when you glance up casually, but when you look more carefully, knowing what to look for, the blue becomes evidence of molecular scattering, stellar physics, atmospheric chemistry, and biological vision all working together. This transformation from simple to complex is the essence of scientific understanding. Science does not make the world less beautiful or less meaningful. It makes the world more beautiful and more meaningful by revealing the extraordinary complexity hidden in ordinary experiences. The blue sky is more wondrous when you understand it, not less. The fact that something so commonplace results from such an intricate combination of factors makes it remarkable rather than mundane. And the sky continues its physics experiments whether you understand them or not. Right now, as you exist, wherever you are in whatever moment this is for you, photons are streaming from the sun, encountering atmospheric molecules, scattering in wavelength-dependent ways, being absorbed by ozone, reaching your eyes, and triggering responses in your cone cells. This happens continuously, moment by moment, day after day, year after year. It happened before you were born and will continue after you are gone. The universe performs these operations without audience or applause. The sky is blue not because anyone is watching, but because physics makes it inevitable. Given a sun of a particular temperature, an atmosphere of a particular composition, and observers with particular biology, blue sky follows as naturally as water flowing downhill or heat flowing from hot to cold. It is an emergent property of the system, not something imposed or designed, but something that arises spontaneously from the interaction of components. Other skies exist elsewhere. Mars shows a butterscotch sky because its thin carbon dioxide atmosphere and suspended dust scatter light differently. Venus shows a yellowy-orange sky filtered through thick clouds of sulfuric acid. Titan, Saturn's large moon, has a thick nitrogen atmosphere like Earth's, but lacks oxygen and ozone, producing a hazy orange sky from organic compounds. Each world tells a different story through its sky color, a story about atmospheric composition, stellar distance, and environmental conditions. Earth's blue sky marks this planet as special, not unique, but distinctive. The blue indicates an oxygen-rich atmosphere, which in turn indicates the presence of photosynthetic life that has transformed the planet over billions of years. Oxygen is reactive and should not persist in an atmosphere without constant replenishment. The blue sky you see is indirect evidence of the forests and oceans producing oxygen through photosynthesis. It is a signature of a living world. Billions of years ago, before life evolved photosynthesis, Earth's atmosphere contained little oxygen. The sky would have appeared different then, probably more orange or hazy, less vividly blue. The blue you see now is a relatively recent development on geological timescales, emerging only after oxygen-producing organisms became abundant enough to transform atmospheric chemistry. The sky serves as a reminder that the planet is not static but has evolved over deep time, shaped by both geological processes and biological activity. This connection between sky color and life's history adds another layer of meaning to the blue overhead. Every breath you take, every time you look up, you are participating in and observing a planetary scale process that has been operating for hundreds of millions of years. The oxygen in the air and the blue in the sky are both products of this process, both manifestations of the same underlying transformation of Earth's surface and atmosphere by living organisms. The knowledge you now possess about sky color is precise and tested. It is not speculation or belief, but established science, verified through countless measurements and experiments over more than a century. You can trust this knowledge to be accurate within the limits of measurement uncertainty. The inverse fourth power law is not an approximation but an exact result from electromagnetic theory. The wavelengths of visible light are measured to extraordinary precision. The absorption spectrum of ozone is mapped in detail. The sensitivity curves of human cone cells are documented and reproducible. This reliability makes the knowledge valuable. When you explain to someone else why the sky is blue, you can do so with confidence, knowing that what you are describing has been tested and confirmed. You are not passing along folklore or mythology, but genuine understanding of how the world works. And should anyone challenge you with the obvious question, why is the sky not violet, you now have the answer. You can explain the 4 factors that shift the color from violet to blue. You can quantify the contributions of each factor. You can describe the experiments and observations that establish these facts. You can point to the research papers and textbooks that document the science. You possess a complete explanation, not a partial one. This completeness is rare in everyday understanding. Most things we think we understand, we actually understand only partially. We know enough to get by, enough to avoid obvious errors, but not enough to answer probing questions or resolve apparent contradictions. The sky's blue is one of those things for most people. They know the word scattering and maybe the name Rayleigh, and they feel this knowledge is sufficient. But as we have seen, it is not sufficient. The complete story is richer and more nuanced. Perhaps this exploration has changed how you will look at the sky going forward. Perhaps, when you see blue, you will think about the billions of molecular collisions scattering short wavelength light. Perhaps, at sunset, you will think about the extended path length through atmosphere and the progressive removal of blue from the direct beam. Perhaps you will notice how the shade of blue varies with atmospheric conditions, altitude, and time of day. Perhaps you will see not just color, but physics in action. Or perhaps the sky will simply remain blue, a familiar constant in an ever-changing world, something reliable and peaceful to look at when thoughts grow tangled or stress accumulates. The sky does not demand contemplation. It exists whether you think about it or not. But knowing why it appears as it does adds a dimension to the experience, a depth that enriches appreciation without requiring constant attention. The universe is comprehensible. This is perhaps the most profound lesson from understanding sky color. The same equations that describe electron oscillations in molecules also describe the electromagnetic fields of photons, and these same equations combine to predict something as concrete and observable as the color you see when you look up on a clear day. Mathematics connects to physics, connects to observation in a seamless whole. This connection is not obvious or necessary. The universe could have been incomprehensible, ruled by whimsy or randomness. But it is not. It follows laws, and we can discover and understand those laws. This comprehensibility extends beyond sky color to everything in the natural world. Every phenomenon, no matter how complex, operates according to principles that can be understood through observation, experimentation, and mathematical description. Some phenomena are extremely difficult to understand and require sophisticated tools and years of effort. But they are knowable in principle. The door is open to anyone, willing to put in the work to learn. You now understand one small piece of this vast puzzle. One everyday phenomenon explained in detail. One window into how the universe works. The sky remains above, performing its continuous dance of light and matter, offering its blue to anyone who looks up. And you understand why. Thank you for taking this journey through the physics, chemistry, and biology of blue sky. If you found this exploration valuable, if you now see the sky with different eyes than before, consider subscribing to continue this quiet exploration of the cosmos together. There are countless other questions waiting, countless other phenomena to understand, countless other connections to discover between the familiar and the fundamental. Until we meet again under these blue skies, may your gaze upward remind you of the extraordinary complexity hidden in ordinary moments, and the profound beauty that emerges when we take time to truly understand the world around us.